Okay, I think everyone's back-ish. Yeah, yeah. In case anybody else gets given a throat ruffle, one of these. Most of you, you've eaten it immediately, and you might have felt a little sick because it's actually like it's very sweet. Do never eat two. But one way you can eat it is if you have your throat ruffle with its 3 layers horizontally. What you then do is you get a cup of tea and place it underneath. And then you have a slightly melted, warmed stroopwafel and a cup of tea, because you want to drink something while you're eating. This is so sickly, you need something to drink. So this is the way, so save one, you get one, and make a cup of tea later. Coffee might work, I don't know.
How do I win a cup of tea?
How do you make a cup of tea? That's a very...
How do I win?
Hey?
How do I win?
How do you win? Yeah, I don't know. Okay. Okay, so the idea of everything I talked about so far was to give quite a broad view of molecules in space. You know, you detect them, where you detect them, maybe a little bit about the conditions that are there. And so now we can look in a little more detail about the main way to detect molecules in space, which is because of their rotation. So this is what ALMA is doing. And I guess the idea was that right now would be 2 o'clock. So you would have had 24 hours since the last lecture. So I can tell you what rotational spectroscopy is for, but you might remember from half an hour ago. Then we can look a little more at the quantum mechanics, because it turns out that we don't want to study quantum mechanics, but if we learn the necessary formulas, then you can really interpret these molecular lines in an accurate quantitative way. Then we're going to learn about temperatures. I'll explain those later, but with not just one temperature, we've got 3 temperatures to worry about. And then we can show how, once you know these quantitative things involving some formulas, then it's possible to make measurements not just of what molecules there are, but actually infer what the environment is, whether they're in a protoplanetary disk or interstellar cloud, just by looking at the molecules themselves. Anyway, that's the idea. So this slide I showed only half an hour ago, and so we're really restricting ourselves to this part of the spectrum. So this is, for a diatomic molecule, you have these electronic states, you have these vibrational levels, but we're looking at this part only. The other thing to remember is that this curve is for a diatomic molecule. So this axis is just this distance, like that. For example, if that was a hydrogen molecule. On the other hand, if you had a molecule of water, so it's an oxygen and 2 hydrogens, you've now got 3 distances to worry about. Or maybe you've got 2 distances and 1 angle, or something like that. Or I don't think it's possible to have 2 angles and 1 distance. That might be possible. So the point is that you can't draw a curve with 1 variable. You have to have a three-dimensional curve, which I'm not going to draw. But that's like it's not even a, if you talk about this being a bowl or a valley, then that's a 2-dimensional curve. So that you can kind of imagine. A 3-dimensional curve is the next number of dimensions up. So that requires thinking in 4 dimensions. But the point is the same picture applies. Rather than have rotational levels in a 1-dimensional well, if you had a bowl, that'd be rotational surfaces in a bowl. If you had a 3-dimensional curve, you'd have 3-dimensional rotational levels in a 4-dimensional curve, but exactly the same thing applies. So we're not always talking about diatomic molecules. Okay, so you could say that the first purpose of rotational spectroscopy in astrophysics is to identify molecules. Because each molecule, this is laboratory results, and it shows, this is gigahertz, so that's the microwave, that's rotations. And for 3 different molecules, sulfur dioxide, I forget, methyl formate, something like that, HC5N. These are all just collected in a gas bottle with a microwave emitter at one end and a microdetector at the other, and you can detect what their spectrum looks like in the laboratory. Pure gases. And the point is that they all look totally different. Even if you take this case, HC5N, which I'll point out because it's an interesting molecule. Because you see these formulas, but they don't tell you what the shape of the molecule is. This one's quite simple. You have an H, you have a C, 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 and you have an N. So that's about the simplest possible way you could write this molecule. Although, as we discussed earlier, each molecule, each atom has a certain number of electrons that bind them together. So we should probably take that into consideration. It doesn't affect anything, but we now know that is where the electrons are as well as where the nuclei are. Anyway, so that's an interesting molecule in any case. And if we measure in the laboratory at 150 Kelvin, so that's already minus 150 degrees Celsius, so it's already cold, but it's still warm by interstellar standards. We measure at 10 Kelvin, we get a different rotational spectrum. So not only can we say different molecules are different, but they're different at different temperatures as well. So this is a hot core. And if you remember, there's a hot core and a cold core. They both form inside giant molecular clouds. They're extra dense areas. But one of them is hot and one of them is cold. And the reason is that if you have a very dense area, it might get so dense that a protostar forms in the center, which makes it hot. The protostar is hot. So you can have a cold core which has not yet formed a protostar, or a hot core that has. In this case, we have a hot core. And we know that because this is a map of an interstellar cloud in the infrared. And it's shining in the infrared because it's hot. That's thermal blackbody radiation. So there's a hot core there. And the object is G327.3-0.6. So remember that. That's going to be in the test. Yeah. Okay, and so at this hot core, they also looked at it with millimeter radiation, so microwave. And you see a whole lot of emission lines in the microwave belonging to really complex molecules in this case. These are molecules which you'd really think might be related to biological systems, or at least organic chemistry rather than inorganic chemistry. And the ones that I've put labels on are all the same molecules. C2H3CN is blue. The name of it, I don't know. CH3OCH3, that's dimethyl something. Dimethyl ether, I believe, maybe. Anyway, so the point is that you have 3 lines from these 2 different molecules, and so those 3 lines tells you is enough information if you go back to a laboratory spectrum and look for those 3 lines in the spectrum to say that that molecule is present. 1 line is not enough. If you knew about this line from the laboratory and you found it in space, it could be that molecule. It could be another one that happens to have the same line at the same place. But once you start getting multiple lines, then you start to identify molecules in space. And also, all these lines have an intensity, how much strength they have. And then you can look at these curves, maybe as a function of temperature, how strong the lines are, and you can say what molecule is there and what its temperature is. So that's the basic idea. This provides a fingerprint for identifying molecules.
It might be a basic question, but I just really don't know.
Yeah?
How do we know which molecule, how do we know each of those lines represent the rotation emission of each of those molecules? We just have like a really big catalog of the emission lines.
Exactly, exactly. Because, I mean, one of the things I kind of didn't say was that, I mean, these lines are really thin and really narrow. So if it was shifted by a small amount, you'd see the difference, right? If you had a really big line and shifted it a little amount, it looks the same. So the fact that they're so narrow, and now the fact that lots of molecules have lots and lots of lines. So if you see 100 lines of sulfur dioxide, all in the right place, narrow lines, the odds of that being misassignment from the laboratory spectrum is just age of the universe type numbers. So, yeah. Yeah. Okay, and so this was the last picture from the last slide showing you the same thing. You're assigning many different molecules. I won't get through them in this case, but also many unknown molecules. That's because there's more molecules in the universe than somebody has created in the laboratory and measured, like I showed, but also because not all molecules are really something you can look at in the laboratory. Like, for example, CH4, that's methane. In this case, you have all the electrons of the carbon are satisfied. This is a very stable molecule. CH3, you would normally create it in a reaction with CH4 plus some kind of energy would knock off a hydrogen. You then have CH3. The problem is that in the laboratory, the CH3 will rapidly react with other atoms and molecules, react with the hydrogen that got knocked off in the first place, and you'll be back at CH4. So creating a sample of CH3 is almost impossible. And that's one of the reasons why these molecules are not known, is because some of them belong to species that don't exist on Earth, even though they do in space. Okay. So ignoring all the details of the electrons, the only thing that really matters to rotational spectroscopy is the rotational inertia. That is how much energy it takes for the molecule to be spinning or not. So in this slide, I've just written up the formulas for this. Idea is that you have a diatomic molecule, but you could have a triatomic molecule with 3 masses in some kind of configuration. And those 2 masses give you the rotational total mass, for one thing. That's useful because if you have some kind of push, the amount of momentum that you generate in the molecule will affect its velocity through its total mass, but that's one thing. It has a bond length. This is exactly on the potential energy curve. The bond length is the point at the bottom. Because a stable molecule will always be at the point of the lowest possible energy, and that more or less gives you the bond length. So that picture and this picture are the same picture, actually. And then the rotational inertia is just a function of this bond length and the reduced mass. So that's not the mass of the individual particle, but the combined masses with that formula. And I thought about going through the formula for the reduced mass. Then I thought I could put it in a test. That might be the other way to do that. Anyway, so it's worthwhile thinking a little bit about this reduced mass for different molecules, just looking at diatomic ones. Hydrogen, so hydrogen is the lightest element there is, just 1 proton by itself in the nucleus. And so it should have a mass of 1 atomic mass unit. Turns out it has a mass of 1.008. I think because the atomic mass is defined in terms of something else, maybe a bare proton, or possibly it was even a carbon atom. But anyway, the point is that it's not exactly 1. But this I put in because it's completely, in most cases, it's not important to what we're about to do. This is too small a difference to worry about. But it's not quite exactly 1, just remember that. And so if you have a reduced mass of 1 times 1 over 1 plus 1 gives you 0.5. So this is a kind of an interesting rule. If you always have a molecule with the same 2 atoms, H2, 2 H's, N2, 2 N's stuck together, then you find that the reduced mass is half of the actual mass of one of the particles. That's kind of a nice thing to keep in your head. On the other hand, if you have 2 different atoms, a hydrogen and a deuterium, so that's 1 hydrogen and a 2 hydrogen, an isotope of hydrogen, then you get a number, fine. But if you get a larger reduced mass when you have a heavier atom, that makes sense. But if you reduce this mass even more, fluorine weighs more than deuterium, chlorine weighs more than fluorine, bromine weighs more than chlorine, you get a larger and larger reduced mass. But it's converging upon 1. So what this is telling us is that if you have a really big atom, like bromine, and a really small one like hydrogen, then then the reduced mass really depends on the hydrogen, because what's going on here is that the reduced mass is to do with rotation. And so if this system rotates, it's really pretty much the hydrogen rotating around the bromine. There's not a lot of other things going on. Where there's a hydrogen molecule, if it rotates, they rotate about their center of mass. So if you make this bigger and bigger, you still have a hydrogen rotating about something heavy. So what this means is this convergence, HF, HCl, HBr, all have about the same reduced mass. And so, as I'll explain later, the rotational spectrum depends on the reduced mass more than anything else. So they all have a pretty similar rotational spectrum. Because when you have a heavy mass and a light one, the light one is the important one. Okay. Okay, so reduced mass gives you a rotational inertia. I'll put it. Reduced gas gives you rotational inertia depending on the bond length. Rotational inertia gives you angular momentum. It's exactly the same as the Newtonian linear equations, but to do with rotation. So I'm sorry if I'm insulting you with this, but it's worth doing. Where in this case we have the rotation rate of the molecule as a function. If there's a velocity and a radius, and you have an angular rotation rate, and that gives you this omega. And I put it out only really briefly because in spectroscopy we can pretty much ignore things like velocity and angular actual time-dependent movements, because we're looking at lines, we're looking at rotational transitions from one level to another. So the only thing that really matters is the energy of that line. Everything else is not measured. So as long as you know what the energies are doing, we can ignore things like velocities and momentums. So the important thing is, rather than worry that we have the energy, in this case we have angular momentum, rotational inertia. We know that rotational inertia is really just to do with reduced mass for a diatomic molecule. So we have a function of energy which is dependent on the reduced mass and the bond length and angular momentum. And then the interesting thing is that in the classical case, fine, that's well, what that would mean, I guess. I haven't followed through all the possible consequences of that or anything like that. But if you could have an energy which depended on a classical angular momentum, then your molecule could rotate at any speed. A photon could be absorbed, make it rotate faster. But that absorption could happen at any wavelength. You'd have a continuum absorption for all the molecular rotational lines, which is fortunately, and this is something I've become convinced of over the years, is that, people think quantum mechanics, or sometimes people think quantum mechanics is kind of hard, like it just, there you are, you're dealing with classical mechanics, you just get it sorted out, and then they throw it all away and have this really complicated theory. But the important thing to remember is that quantum mechanics is actually easier than classical mechanics. In quantum mechanics, less things happen. The universe is simpler. If we had to try and solve real-world problems purely with classical mechanics, I think there's not enough. There wouldn't be quantum computers to help us. We'd have to use classical computers, and we'd never get there. Anyway, the point is that the angular momentum is the fundamentally quantized thing in rotating molecules. And exactly like the case with the hydrogen atom, we discussed that. A rotating molecule, just like that, and we can think of its path as being rotating, and we can think of its position as not being two particles, but it's a wave rotating along the trajectory. So somehow this is a wave, like that, and exactly like the hydrogen electron, it has to be a matched phase around the path. That means there has to be a whole number of waves around the path, and that restricts the possible number of. This is the trajectory around the thing, beginning at 0, finishing at 2 pi. Then we can draw a wave extending across this path, and so we instantly have a quantization. Because we have a closed boundary condition, we don't have any possible angular momentum. we have one which depends on a quantum number, just integer values. And one thing to remember is that the first wave is this one. The first wave is no wave. You can always have a flat line, basically, which is not particularly important in this case, but worth remembering. Anyway, so each of these J's, number 0, 1, 2, 3, corresponds to a wave with more and more oscillations. We won't go into that anymore, but that's why it's easier than classical mechanics. I mean, we didn't have to calculate anything. We just know logically a wave has to have a matching phase at the ends, which maybe is an assumption, and you can get this formula. Okay, so that's quantized. We put it back into this formula, L, Jj plus 1. You get energy as a function of Jj plus 1 here. So then energy is quantized. And so energy is the important spectroscopic parameter. As convenience, we have all these values, h bar squared, that's Planck's constant, reduced mass, the bond length. Just put it into one number b, just for convenience. And then we can draw the energy levels as a function of energy, up here, sorry. And yeah, and so they get separated further and further in space because Jj plus 1, that's basically, well, it's basically a quadratic formula. Jj plus 1 is close to j squared. So these levels get further and further apart as j squared. Even I've conveniently drawn on here what these levels are as a function of b. J equals 0, you have a 0 level. J equals 1, it becomes b times 1 times 2, 2b. J equals 2 becomes 6b. So you can actually just, once you know the b parameter, you know all the levels. That's why I said when you know the reduced mass and the bond length, you've got the rotational spectrum, because you know all these levels. Which would be awesome. But was that a, no, you're reaching around. Except that things are never quite so simple. And the problem is that if you have a molecule bound together by electrons, of course, if you had just two positive charges, they wouldn't be bound at all. The electrons are somehow holding them together. And if it rotates, then there's the electrons, but also there's the fact that there's a centrifugal effect pulling the two molecules apart. Or alternatively, there needs to be a force pulling them inwards to pull them together. And what that means is that they actually move outwards slightly. And so that can mean that the bond length will increase. There. So if you have increased bond length, energy is going to go down. So you need a correction factor. Minus d, d's the correction factor, reducing the energy levels. And the reason this is j times j plus 1 squared, angular momentum is j. And so the more angular momentum you have, the more centrifugal effect you require. And so there's a kind of a squared factor there. There's another way to look at this, if you prefer things mathematically or more abstractly. So if this is a diatomic molecule, this is the distance between them. The molecule sits there because it's in its most stable point. If you add centrifugal energy, or you're adding another term, 1 over r squared, which means that this curve changes shape slightly. And so now, by adding the energy to the potential energy, which otherwise is just the electrostatic force of the electrons and the protons, you have a shift in the bond length outwards because you're adding a centrifugal amount of energy as well. Anyway, the important thing really for this course is that you have a b value, which gives you this nice level structure, quadratically increasing, with a correction factor, the centrifugal distortion parameter, d for distortion, which makes it not such a nice formula anymore. It pushes them back down.
Sorry, can you explain again what does the b factor?
So the important thing really is reduced mass and the bond length, and that comes from the fact that the energy is the square of the angular momentum divided by rotational inertia. Angular momentum, which is from quantum mechanics, must have this formula. That's kind of usual thing. provides the jj plus 1 and the h bar squared. And so this really is just coming from the classical equation for rotational energy. And so we call it B rather than h bar squared over 2 mu r squared, because in the laboratory you could measure these levels pretty easily in many cases, but you might not know the bond length or you might not know the reduced mass. So in principle you might know B but not the other parameters. In reality you probably know the reduced mass already. So a very common thing actually is to measure B in the laboratory, these energy levels, work out what the reduced mass must be because you know what molecule you're looking at, and then you know the bond length. So it's actually really easy. This length is usually about, I don't know, 0.1 nanometers. So not much. There's no way you can ever look at it with a microscope. But because of this formula, and because of these levels you can measure, like I showed you rotational spectrum, you can measure the bond length pretty easily in most cases. Yeah. So welcome back. So okay, so some other examples which will turn out to be important later on. If we try and calculate what the B value is. So that's a bigger B value, the levels are separated more in energy. And the key thing to remember is that the bigger the mass, here I've got hydrogen, the lightest molecule you can possibly have, carbon monoxide. The masses of carbon is 12 atomic mass units, oxygen is 16. That's probably the most important astrophysical molecule, so that's why I put it in that list. And it has a B value which is 30 times less than hydrogen, which turns out is a massive difference. Iodine, I2, has a mass of 127. This is completely irrelevant to astronomy as far as I know, but I wanted to put an even smaller rotational constant on this graph. And distortion constants, they kind of follow their own logic. That's a more complicated property to work out, but they have values significantly smaller than B. They really are a small correction in most cases. Okay, so those are all diatomic molecules, just 2 atoms. So we can work out the rotational inertia as a function of one parameter only, r. But the same thing happens for more complex molecules like water. You have 2 hydrogen atoms on an oxygen atom at an angle. And the point is that now we don't have just one distance to consider, we have 3. And we also have 3 rotational inertias. Rather than just one reduced mass, we have 3. And I won't go into detail, but the point is that this is exactly the same graph, as this graph. J is increasing and energy is increasing, except something is clearly more complicated here. Like this is energy going up. These levels are labeled with J. J equals 0 still at the bottom. J equals 1, 2, 3 increasing. But they now have other quantum numbers associated with it as well. One number is no longer enough because you have a complex molecule, you have 3 rotational inertias all working together. And so this there is actually no formula for this situation. It's possible to calculate these levels using kind of a non-closed analytical method. You have to do some numerical work to do it, but you can do it. Or alternatively, you can just measure it. Like everything we're describing, if you're purely interested in identifying molecules, you just measure the molecules, look in space, there it is, your job is done. But we can do a lot better if we understand some of these things as well. So the point is that most molecules, which are not just N2 or H2, have a much more complicated structure. The nice thing is that it's not really about the fact you just have 2 atoms. It's about how symmetric your system is. So if you consider it again, HC5N, which I showed before, this is still a straight line. And the symmetry of this and the symmetry of H2 is the same. So it turns out that any molecule which has the straight line linear structure has the formula of the simple formula. Okay. So it's going to turn out that the energy levels are important. Degeneracy is also important. And I couldn't figure out the right way to draw waves on a graph to describe the right amount of degeneracy. I'm sure there is a way to have a simple description of why you get this formula is the way it is, but I couldn't give it. The point is, though, that you have a if you have a rotating molecule, it has angular momentum perpendicular to the rotation direction. That's the property of angular momentum. And as we described earlier, there has to be a wave, a whole number of waves in this rotational direction. That's what gives you the quantized angular momentum. Like that. And because we're in three-dimensional space, this wave is actually a three-dimensional wave, which means that it has to have a, call this formula angle theta, and we have another. It has to have a secondary direction, which also is satisfying the correct number of nodes of a wave. That's it. That's not even a good explanation. I'm sorry, I can come up with a better one. The point is, though, that the direction of your angular momentum in three dimensions is quantized. You have 5 different ways to, in this case, to have a J equals 2 J equals 2 rotational level. That's the 0-1. They have 5 different directions they can point in. If you have a J equals 1 level, you have 3 directions. There's a formula. The number of directions they can point in is just 2J plus 1. So what this means is that you have a molecule which have a rotational level, or it can have another rotational level which is the same angular momentum but a different direction. Okay. That's not quite the end of the story, unfortunately, because there's not only angular momentum from the fact that you have a rotating molecule, you have angular momentum internally to the molecule as well. And the picture here is that if you have a hydrogen atom, this is the drawing of the 2 hydrogens, and those hydrogen atoms have magnetic moment. They themselves have a small angular momentum intrinsically, like electron spin. And so that's providing an extra component to the system, and it means that they can have hydrogen proton spins which are pointing in one direction or another. And it turns out the important cases, which I won't go into, is whether the internal angular momentum of the hydrogen atoms point in the same direction or the opposite. And that has a direct effect on this degeneracy. So the degeneracy depends on the angular momentum, J, 2J plus 1, times another number. And that other number depends on this. And so here I've made a table. And it turns out that hydrogen, which is a fermion, that means it's just a proton by itself, has so much angular momentum, a value of 1/2 d, and 14n, another molecule, are bosons, as well as oxygen. These are unnecessary details, but I put it on the graph. And what that leads to in the end is that this F factor depends on the molecule, and it depends on whether J is an even number or an odd number. In case of hydrogen, the J equals odd levels, that's J equals 1, 3, and 5, are 3 times more degenerate. There's three times more of them than there is of the even levels. We can explain that in more detail later, but it seems kind of necessary. And there's a couple of strange cases. Carbon dioxide, the degeneracy number for odd rotational levels of carbon dioxide so carbon dioxide is a straight molecule as well. It's linear, so it has the same formula as H2 and so forth. It's a linear molecule. Carbon dioxide has a value of F which is exactly 0 for the odd levels. So what that means is that if you go back to this graph, for carbon dioxide, this is J equals 0, that's even, J equals 1 is odd, blah, blah, blah. These levels would be missing completely from the graph. So because of nuclear spin, some of the levels are missing. Okay, that's it. Just remember that for the time being. That's interesting. Okay. So those fundamental formulas, which I have not explained in a proper derivation of anything really quantum mechanical, hopefully will be useful. Okay. So going back to classical physics, we're now talking about kinetic energy distributions. If you have particles in a box in the room, they bounce off each other, they have a certain amount of energy, they're moving, And so the velocity distribution of these particles, some are moving fast or slow, depends on a Maxwell-Boltzmann distribution. I won't even put up the formula, but the point is that if you have the velocity of particles in this room in kilometers per second, so it's fast, and this room is, well, okay, this is 100 Kelvin, that's somewhat colder than this room. The velocity of the particles are mostly about 1 kilometer per second, that's fast, but some of the particles stretch out to much higher velocity, some are much lower. That's all we need to know. If you have the same particles, hydrogen atoms, in this case, assuming they're hydrogen atoms, cool it down, the velocity becomes lower, so forth. If we have the same temperature, 100 Kelvin, but we make these particles not be hydrogen atoms, but methanol molecules, the important difference being their total mass. Hydrogen is a mass of 1 atomic mass unit, methanol is a mass of 30 atomic mass units, then this curve also shifts down. That's because the same amount of energy means that it gives you a lower velocity distribution, and it turns out velocity is what's more important in a lot of what we're discussing. Okay, so remember that, Maxwell-Boltzmann distribution for particle motions. And the important thing is we define this as the kinetic temperature, kinetic meaning movement, and give it the symbol T with a little k. There's another important effect here as well, which is the Doppler effect. The idea is that the molecular energy levels that we're looking at, all the spectral lines we'll be looking at, are dependent on frequency. And as you know from the example of the redshift, if you have something moving away from you, the frequency shifts. Similar, if we have this distribution of velocities, that gives us a spectral shift individually for each molecule in the box that we're observing emission from. Meaning that if we have emission lines, there's 3 of them, then the molecules have a distribution in velocity, which is just shown by this graph. And that distribution of velocity also gives you a distribution in the width of the line that you observe with a telescope. So often you see velocity is used as a unit for frequency. I mean, okay, and so these 3 examples, we have hydrogen atoms, hotter and colder, gives you more or less width, because these velocity distributions become wider. Methanol gives you a very quite a thin line, because the velocity distribution is less. And the other interesting thing, not only do the lines get wider, because you still have the same number of particles in the box emitting radiation, the lines must get lower, because the integrated area is what we're observing mostly in the spectrometer. Okay, so 2 interesting things about the kinetic temperature and velocities in the box. Just the definition, really. Okay, so that's one temperature. There's another temperature, the excitation temperature. Give that the symbol T with a little EX. And what this graph is supposed to show is the particles in a box rotating, because it's rotation that we're interested in mostly. And so they're moving around at different velocities, and they're also rotating at different velocities. And so the formula for the Maxwell-Boltzmann distribution was that curve. I didn't write the formula, because that wasn't so interesting for us. But what is interesting for us is the formula for the rotational distribution. How many molecules are rotating quickly or slowly? And the formula is given by another Boltzmann distribution, where now we have Nj. So, yes, let's write that up. So the total number of molecules in this box has a number, which we'll call N. And we can divide that up into molecules that are not rotating, some of them. Molecules that are rotating with J equals 1, remember they can only have certain levels, and then J equals 2 and J equals 3. In the case of carbon dioxide, we wouldn't have to worry about this part of it because there's no odd levels for carbon dioxide. So this distribution is telling us what is the value of each Nj in that distribution. And that's going to depend on the energy of each level. And we saw a formula for the energy of each level. That's the exact formula. It's going to depend on the excitation temperature. Okay, we're describing excitation temperatures. It's going to depend on the degeneracy also. So we saw a formula for the degeneracy, kind of a physical explanation for it, but not a very convincing one, I admit that. And so therefore, you already have enough information to describe this part of the formula telling us how many particles there are in which of these part of this population of rotating particles in the box. The value Z tells us how many there are in total. If you add up all these distributions, in a summation, we get the total distribution of particles in the box, just as a normalization factor. Okay, so that's the Boltzmann distribution. As a function of excitation temperature, we know how many particles are rotating at each value of J with each energy. But often more interesting than worrying about this factor Z at all, if we just think of two rotational levels. I won't even write that up. If you think of populations of two rotational levels, nj1 divided nj2, then the division becomes a subtraction within the exponential. This formula tells us if you want to know the j equals 1 rotational levels, j equals 1 population in the box with the j equals 2, we have a simple formula which depends only on the energy of the two levels and the degeneracy, which I left out, and the excitation temperature. Okay. And so this is the shape of the Boltzmann distribution of rotational levels. It looks pretty similar, this one at least, carbon monoxide, to the Maxwell-Boltzmann distribution. It kind of has a few low values, a peak, which depends on the temperature, and a lot of high values. Doesn't look very similar when you start looking at hydrogen. And the reason for that is that you no longer have all possible rotational levels in between, you can only have the discrete values, so you get a sampled kind of curve. Okay, which depends on temperature. A lower excitation temperature, you have lower energy levels excited. Okay, and the basic idea is that these two temperatures, between the kinetic temperature, the velocity of the particles, and the excitation temperature, and remember that kinetic temperature we can see in space by how wide the lines are, that's the Doppler effect. In this case, we just have a different distribution of rotational level populations. And so these two temperatures in this room are always exactly the same. The reason being that if you have enough collisions between particles, the thermodynamic equipartition principle means that energy, whether it's rotational energy or velocity kinetic energy, is spread evenly throughout all particles in the room. In space, that's not the case, because that assumption that we make all the time depends on the collisions between particles, it depends on density, and because there's a low density in space, this is no longer always the case. But the case where the excitation temperature and the kinetic temperature are the same is thermal equilibrium. Okay. So that's all to do with particles colliding, but we also need to consider now the spectroscopy. In general, we've discussed. Oh, yeah, sorry.
One question. At this level, is still valid the principle of conservation of the mass?
Principle of conservation of mass.
I know it is not true because, for example, the electron, positron, and inflation, but at this level, you can use them. You can use it, for example, for analyzing conservation of momentum, or using this principle to see other things of the system.
So you mean if you have a box with particles in it and particles are appearing or disappearing?
No, I mean, if at that level we can assume that no particles are destroying.
Definitely. Yep. That would be much too complex for the astrochemical world to worry about particle and annihilation. You mean actual antimatter things? There are experiments actually. This is well out of what we're talking about. There are experiments to do spectroscopy, rotational spectroscopy, or electronic spectroscopy of antimatter. So in this case, rather than have a hydrogen atom, you have an anti-hydrogen, anti-nuclei, anti-proton with an anti-electron orbiting it, and you can do spectroscopy on that. And then you're looking at fundamental physics, that kind of thing. But in this case, no. We're in non-destruction of matter regime. Okay. Okay. Photoabsorption. These are two energy levels of a molecule or an atom. I've called it E rather than J because it might not be rotational energy levels. It might be vibrational energy levels or electronic energy levels. And the point is that we still have these densities within the box of energy levels in the lower state or the higher level. So there's the total number of particles is the sum of these, but it's divided up. And photons, by definition in photoabsorption, are absorbed by a molecule, whatever the shape of the molecule atom, whatever's going on, and excite the particle into a higher level, increasing the population in the higher level in your box, and absorbing the photon in the process. That's all the processes, meaning the spectrum shows a lot of photons, with some photons disappearing at the energy which corresponds to this difference. That's what the line is. The important formulas in this case is just that we can write this as a differential equation. If we have the number of particles in the upper level, the number of particles in the lower level, that's changing with time if a photon comes along. So if one particle moves up, then we have the number of particles in the excited levels increases, the number of particles in the N1 state decreases, and that's just proportional to the number of particles that were here in the first place. Rho, which is the energy density of photons, so the number of photons basically, and then a parameter B, the Einstein absorption coefficient, which is what's specific to that particular molecule. So each molecule has a probability the photon will excite it or not, and that depends on the details like the electrons and the structure of the molecule that we've been talking about. Okay, so that's all it is. The Einstein absorption coefficient depends on the molecule, but otherwise we just have the normal differential equation looking at the number of states in the lower state or higher states. Okay. Photoemission is exactly the reverse process, where the molecule loses energy, drops down a level, and a photon appears. Energy is conserved in terms of a photon being created. So now you have the intensity of a radiation field being added to, as long as this energy corresponds to this energy. Extra photons are appearing. But you have two cases which are actually important in astronomy. The spontaneous emission, this is what occurs in fluorescence in general. If you see spontaneous emission from the sun, from a black body, or spontaneous emission inside a light bulb, and stimulated emission, where a photon promotes emission faster than normal, creating two photons, which is what you have in a laser. And this actually does happen in space. It doesn't happen at a frequency which you can observe like a supermarket laser, but you see the same effect in microwave transitions. You have a microwave laser generated within an entire interstellar cloud. It's kind of, I wasn't going to talk about that, but that's kind of an interesting subject. Okay, so these can also be described in terms of a differential equation describing how many levels, how the population is changing in the upper and lower levels of all the particles in your box. In this case, it decreases by the proportional to the number of levels in the upper state. Because it's a spontaneous process, it doesn't require any external influence. It only depends on the number of levels in the upper state. And another parameter which is dependent on the molecule, the Einstein A coefficient, which is once again depends on all the details of all the electrons in the molecule. In the case of stimulated emission, you depend not only on how many levels in the excited state, but the number of photons that are coming in during the stimulation. So you have a dependence also on the energy density of the photon field. And another constant, the Einstein stimulated emission constant. So that's three different constants describing the three ways a photon can be absorbed or emitted by a particle. Okay. Okay, so in general in spectroscopy, then you always talk about energy levels first, and then you talk about transitions afterwards. So this is exactly the same graph as before, showing the energy levels of a rotating molecule getting further and further apart. And now if we then discuss the emission of radiation within this molecule, we're talking about falling down these energy levels. And each step down produces an energy in the spectrum, an extra photons in the spectrum, which depends on the energy difference. And this is the key thing, because this is a quadratic series of energy levels. The J plus 1 is approximately quadratic. That's that dependence. Then if you take the difference of those quadratic levels, you get evenly spaced rotational lines. The JJ plus 1 subtracted by the lower JJ plus 1 gives you an even spectrum. So you actually have, in the ideal case, ignoring centrifugal distortion, ignoring the stretching of the molecules that rotates, evenly spaced rotational lines. And the important thing here is that I've drawn here only emission which is falling down one rotational level at a time. In principle, you could have emission from j equals 4 down to j equals 2. And this does actually happen, but by far the most important case is when delta j equals plus or minus 1. And this is because I'll discuss this a little bit later, but the photon has some angular momentum of its own. And in the most common form of interaction with matter, it'll transport exactly 1 unit of angular momentum, j equals plus or minus 1, to the molecule. It'll either add to the molecule's angular momentum or subtract from it. That's because of the fact that angular momentum is actually a vector. If you have a rotating molecule, we say it's rotating in this plane, but more accurately, it has angular momentum at right angles to that. And so the photon can either bring in its own angular momentum and either add or subtract to the angular momentum of the molecule. So there's kind of because you're dealing with a vector quantity, you can have both things happen, which means that delta j equals plus or minus 1. In this case, delta j equals minus 1. It's always going down. That's emission. Delta j equals minus 1 is photoemission. Delta j equals plus 1 is going the other direction. Yeah. So that's photoabsorption. Both cases happen. Okay. Oh yeah, and so I think I was then going to remind you that we saw a laboratory spectrum of rotational spectrum of a molecule at different temperatures, and the spectrum changed. And that's because of the populations. I mean, if you have a very high excitation temperature, you have a lot of molecules in the high rotational levels, which means you see a lot of the rotational emission from the highest transitions, down, down, down. If you have a low temperature, they're all more in the lower levels. And so that's why you see that. Okay. Yes. This point I will discuss in the next slide. Okay, so another point is that I wrote down the formulas describing differential equations, talking about how these populations move up and down in the cases of photoabsorption and emission. And the parameters that are involved was an Einstein B coefficient, which is the stimulated emission, an Einstein B coefficient, which is the spontaneous emission, the absorption, and an Einstein A coefficient describing emission. That's 3 constants. That's confusing. So it's worthwhile going a little deeper and trying to reduce the number of constants, because it turns out they're not all necessary. Oh, but it's 5 o'clock. So you can enjoy hopefully with looking forwardness, looking at the slide, these formulas, or maybe you can, with a little fear, but that's not really unhealthy as well. And we'll discuss the electric dipole transition moment in the next time, because 5 o'clock is our scheduled time. There was supposed to be notes printed out for you today, but I think Jorge didn't get my email. Oh, there is. Oh, all right. Okay, great. And there might even been some. Yeah. Okay, great. Well, we'll stop here. This is exactly halfway through, so I guess we've got another an hour of this next time, and then actually, my original program was to stop with me telling this stuff to you, and you can do some work actually in here on the computers as well. So it'll be hopefully a little more interactive. And yeah. I think we'll stop there. The next time we start again is on Thursday at 9, tomorrow being a holiday. And yeah. Thank you.